Haley Mullins, Michaela Madsen, Riley Offing, come to the office, please. Haley Mullins, Michaela Madsen, and Riley Offing, please come to the office.
Need your notes today, and then that worksheet if you still need work. All right.
I told Carly what my mom told me. She's like, yeah, that's not Sabrina. What does Sabrina say? She's the one that knows. I was there. Yeah, she was there.
Alright, need your notes today. If you haven't finished that worksheet that I handed out on Friday, or if you need it, let me know, I'll give it to you. That was the one that we got Friday, the end of class, and it's due, I believe, Wednesday, and you have to do some proofs. So does anyone still need that worksheet? Okay. Who's right behind you there, Ben?
Bailey.
I think she warned me. Remember that. All right, so how about your notes? We'll go through it here in a second. Okay, just a few notes today, not too bad. Then I'll give you some time where you can kind of work on that worksheet together and stuff. Remember, you need your property sheet for that. For that worksheet. Probably what we're looking at this week, kind of the schedule of events. We're looking at like 2-7 today and tomorrow. 2-8 maybe Wednesday, Thursday, and then we'll start the review process for the test that we'll have in Chapter 2, and that'll be next week. I'm thinking maybe next Tuesday, so you have about a week notice. So you'll get your practice guide maybe Thursday this week from the sub, and if the sub doesn't give it to you, because I'm gone Thursday, but if the sub doesn't give it to you, then Wednesday or Friday I'll hand it to you, and then we can go through it. Because Friday and Monday will become the review day. Thursday should be just a work day to work on kind of wherever you need to, the homework that we're going to get from Wednesday and stuff. So not too bad. That worksheet that I gave you is due Wednesday this week. So that's the one on proofs. You only have to do the first 5 problems. That's it, 1 through 5. Don't do the back page, because you guys took notes, so that was kind of a reward for doing that. All right. So section 2.7, proving segment congruence. So we're kind of moving on. We're going on to geometric proofs. So that's kind of the idea. So here's kind of our goals today. We're going to do a quick review of the properties that we needed for that worksheet. The properties of algebraic expressions and equations. So we're going to go through those real quick. I'm just going to give you the 2 slides, just so when I post this online today, you have a kind of a quick review of what those property names were. Then we're going to do an example of proofs. We're going to do at least a couple geometric proofs. I might review one that we started Friday, but we never finished. So we'll go through that, and if we need to do another one, we can. Just to show you kind of how they're basically the same as an algebra proof. But remember, since you've proved on that worksheet that you're working on for Wednesday that you can do all the steps for algebra, we can start to shortcut these up. So we can do just the basic properties. So that's kind of the nice thing. Okay. Then we had postulates 2.8 to 2.9. That's these are the 2 that we're going to talk about today, and theorem 2.2. So if you don't remember what the postulates were before this, 2.1 all the way to 2.7, they were based on lines and linear equations. So like segments, lines, planes. We had a bunch of them talking about intersections when certain segments and lines meet. So those were all the postulates we had. The theorem 2.1 that we had was on midpoint. So if you can kind of remember back to that, where it talked about midpoint. So these are going to be our 3 things we're going to cover today. And if all else fails, we'll try to do a couple examples of this later. I'm not sure if we'll get there today. So this is kind of where I put my outline today. This is what I want to get to today, is through these, which shouldn't be too bad. I don't know if we'll go further. We'll kind of look at the clock and see, because I want to give you some kind of work in that worksheet today with some people. So, all right. Any questions, comments with what we're doing? Okay. Let's start with these two properties, the quick review of that, and then we'll go into some geometric proofs. You can see how it works. So, real quick, these are the properties of equality from your handout, that study guide that I give you. Remember, that study guide you're allowed to use on the test, but you can't add anything to it as of right now. So what we're talking about here is reflexive properties, symmetric, transitive. These 3 we're actually going to cover today. I actually want to show you how these work for a geometry proof today, because we haven't really seen these. I think we did an example of how symmetric works, but never reflexive and never transitive. So I said they applied basically to the geometry proofs. Then these additive properties of equality, where you can add stuff, subtract stuff, multiply and divide things to both sides of an equation. So those are the ones we did last week. Then we had the field properties. These are the ones we really introduced from Monday through Friday last week. Closure was called substitution. We had commutative property, associative. These we kind of really looked at the end of the week last week, like Thursday and Friday. We really looked at those, how those worked. The identities, there's 2 of them. This is where you add 0 and multiply by 1. And then the inverse is when you make 0 and you make 1 by either adding opposites or dividing numbers. And then distribution, we talked about how to do that correctly, where it takes 3 steps. You distribute, you associate, and then you substitute those numbers in. Okay, questions, comments on any of these? Okay, they're on your property sheet. You definitely need them. All right, let's talk about a geometry proof. I do want to do at least 1 or 2 of these right now. So this is a problem that I showed you Friday, but we never did. So here it is. So we're going to write a 2-column proof for the following problems. So here's the example that I want to do today. So if the segment AB is equal to BC, or congruent to, I should say AB is congruent to BC, then X is equal to 4 on this picture. And we're going to try to show, is this true or false, because it's a proof. We got to show, does this work? This is kind of our thing. So we have our conditional statement, if-then statement, and we have the picture that goes with it. Okay, now, how do we start geometric proofs? Yeah, so that would be one of the first steps, right? So we're going to write the word proof here. All right, and line 1, we start with what we're given, and then the next line is we define what congruent means. That's like how they always kind of start. So AB, this segment here, is congruent to BC, that segment, and that was our given. Now notice I didn't write X equals 4. That's the last one. That's what we're trying to show. Then our conclusion, what we want to show, the then part, is X equals 4. So that should be a couple lines down, maybe 4 or 5 lines down. Okay, that's the idea. Again, we're just doing basic substitutions and properties here. Nothing like crazy in depth. So line number 2, you can hear Trish here. She said we have to define congruent, which you're right. So what does congruent mean? Or equal. So that means the segment AB, the length of that segment. Notice I leave the bar off of it. That means the length of it, the distance. The distance for AB is exactly equal to the distance for BC. So that's what that means. And this is the definition of congruent. That the actual distances are the same, or the measures. And again, since those segments, I don't need to put a little M out front, as those are triangles. And now that we have that, now I can jump to the picture. So what is AB on that picture? Yeah, let's substitute those in, and that's actually the property I'm doing here. So 3x plus 15, and BC is 5x plus 7. What we're doing here is we're substituting. Substituting things with equal value in. So instead of writing AB, we can write 3x plus 5 because that's the actual distance. And so now you can see now it's an algebra problem. So now we can solve this thing and see if it actually works. It might take maybe a couple more lines, but we're going to do just the basics. We're not going to go in depth and showing, property opposites and additive identities, and we're not going to do that. Just what is the basic thing we need to do to both sides? So I need to solve for x. So I don't really care how we do it. You want to move the x's to the right or the left? Which way do you want to go? Where do you want your variables to be? Right or left side? Left side. Okay, so we'll move everything to the left side. So for the variables anyway. So that means I need to subtract the 5x to this side, which is fine. And I'm going to subtract the 15 to the other side. And what am I technically doing to both sides? Subtracting. That's the property D. So in line 4, we're just going to write down what the answer is for when we subtract. So when we actually subtract here, we'll get a negative 2x. The 15s are gone. The 5x's are gone. What's 7 minus 15? Negative 8. And all this property is, that's the subtraction property of equality. This is how I told you, when we do geometry proofs, we can kind of shortcut a little bit. We don't need to put every property, because since you prove that you know what all the steps are, you don't need to show every single one. We can kind of shortcut. All right, questions with what we've done so far? Okay, we only really have one more line to go here. What do I need to do to both sides? Divide by what, negative 2? So let's divide both sides by negative 2. And when we divide, we'll divide this side by negative 2. We'll divide the other side by negative 2. And what we'll get is we'll get x equals, what, 4? And that's the last line. That's what we're actually trying to show. That exact thing. That's what we're trying to show. X equal to 4. So that's why I put the dot there. That means therefore. And what do we do to both sides? We divide it, right? So that's division property of equality. And there you go. Now, obviously, the rules we're skipping. We're skipping, when you divide both sides, we have to do substitution to one side. We have to do, a reciprocal to the other, multiplicative identities. And we're skipping all those little steps in between. But these are the main properties. That's the idea. Okay, questions, comments on any of these geometry style proofs? How they work? Okay, now that was one. I think I showed you the picture on Friday. I thought it was kind of a good thing to go through it one more time so you can see it. Geometry proofs tend to take about 4 to 5 lines usually. I mean, I can think of if you were to attempt to do this problem a little bit differently. Like if you're that person that wanted to move this 3x over here and move this 7 over, it would take you maybe 1 extra line because we would have to switch the answers because we have the x on the wrong side. Because I need to get my answer to look exactly like this. But it's not a big deal. It's the same concepts. Okay, questions on geometry proofs. I think a geometry proof is almost a little bit easier than an algebra proof because you don't have to do so much work. It's just the basics. I mean, the setup is usually always the same. You start with what they give you, kind of redefine that, and you just do some math after that. So it's kind of easy. We'll get to harder ones later, but I mean, this is kind of the start of it. All right, let's jump in. Let's take a look at maybe another one. I might not do the next one, but I want to at least show you that so you can kind of see how geometry proofs are always kind of the same setup for right now anyway. Until we get to really the hard theorems and stuff. All right, So next, so here's another example. We're not going to probably do this one, but so the example is, angle y is equal to angle z. I mean, congruent to an e, and we had to prove x equal to 100, and you can kind of see the picture. So it's the same setup, right? Line 1, you write the given. Line 2, you redefine what that means. Line 3, you substitute these things in there because those are the measurements. And then you do some math where you subtract both sides, add both sides, and eventually we get x equal to 100. And it takes about 4 to 5 lines again, but it's the same exact concepts. Okay, questions, comments on any of that? Okay, again, if you want to see me do one of these, that's fine, we can go through it, but I mean, it's the exact same process. So I just want to show you kind of different examples of that. Okay, so today, what we're going to talk about, there's 3 things on the kind of the bullet list that were new. I want to talk about postulate 2.8, postulate 2.9, and then theorem 2.2. Those were like the main things on the docket that I want to talk about today. That way I can give you some time where you can work on your homework, right? So postulate 2.8, we'll go through this. This one does have a name. So I will put the name up here in a minute. For right now, I want to see if we can figure out what the name of it's actually called as we go through it. Okay. This one may not be as obvious, but the next ones are. So this one does have a name. It's one of those first postulates we get that's actually super important. It may not seem like it, but it is. All right. So here's the word. So the points on any line or line segment can be put into one-to-one correspondence. What one-to-one means for every like point, there's exactly one letter or number that can go with it. So it's a perfect one-to-one relationship. So every point you pick, there will be a number or letter that's associated with it. That's what it means, one-to-one. Perfect correspondence with a real number. So we're actually using numbers here, not variables. So any point on line or line segment, this is a big deal. It's any type, you can put a one-to-one correspondence. Okay, bless you. Okay, now, to explain that a little bit further, because that doesn't really tell you a lot what this postulate means. There's a second line that they talk about. This really explains like what they're talking about here. So when you're given 2 points, an A and a B on a line or a line segment, wherever you pick. So you have an A and a B. You can pick A to represent the number 0. So if you're drawing this by yourself, I can pick A as 0, and B can be any other positive number that you want. So it just says any positive real number. So it could be a decimal or fraction. Once you have those two established, what you have now is you have an entire number line. You have this. So that's the big deal. So what they're trying to explain to you is that we can draw a number line any way you want, as long as you establish the first 2 coordinates. Then it establishes the rest of them. You know the spacing, you know all the terms that are involved. So this was just a rough example. This is just a picture of someone's book. But what this is actually telling you is that that if we were to pick so any line or line segment, and I pick A on there. So here's A. A is the number 0, right? And I can pick B anywhere I want. And that could be any positive number. So that could be, the number 2. Now you have the number line established, and you can now draw all the rest of the numbers off of it. Which, this is the goofy part. So this is 1, that's 2, this is 3, this is -1, that's -2. Now why does that look goofy to you? Exactly. Right. Usually, like when you think back to elementary class or junior high class, right? The positive number is always on the right, the negative number is always on the left on a number line. But why did they always have to be there? This postulate says it doesn't matter. You can draw a number line any way you want. Negatives on the right, positives on the left. As long as what they're talking about is that you have perfect spacing between numbers. So you establish the first 2 numbers, and now you have the spacing for the rest of the picture. And it can be any 2 numbers you want. So, where the letter C would be. So there's A, here's B. C would be down over here, and this would be the number 4, and this would be the letter C. So now you have the spacing all established, and you go off of that. Make sense? So the first 2 numbers really pick that. So now if I go to the picture that I showed you a little bit ago. They picked A as 0. So let me show you that. So here's A is 0. They picked B as 3. So what would C be down the road? 6. So you already have like this in your head. You already have established what the number line is. It's going by multiples of 3. So 0, 3, 6, 9, 12, and you can figure out all the rest of the letters. So this is just, I thought this was interesting. This postulate that it establishes that you can draw a number line any way you want with any numbers, as long as that every dot you pick has a perfect number that goes with it. Okay. Now, the actual name of this postulate is called the ruler postulate. Now, why they call it a ruler postulate is that you're actually establishing how to draw a ruler for the first time. Now, obviously, like rulers that you guys see, like the rulers that I have over here, they're already pre-manufactured, right? They're 1 foot long. They have certain markers on there, like you're seeing here. Okay, but we could have established the ruler at any size we wanted. Like the difference between the U.S. customary system and the metric system, right? The U.S. customary system uses inches like this. So we have inches where, this is a half an inch, that's a fourth, that's a 3/4. We have eighths, 1/8, 3/8, 5/8, 7/8. Anytime, like on a number line for the customary system, the markers that are in between whole inches, they always go by odd numbers, which is really goofy, right? So this is 1 out of 2. This is 1 out of 4. 3 out of 4. The top number is always odd. The bottom number on your fractions are always even numbers. So it's halves, fourths, eighths, 16ths. But the top numbers always go by odds. So 1/8, 3/8, 5/8, 7/8. So you can see how that works. That's how most people never realize that system. That's how the U.S. made their number lines. Okay? The metric system uses multiples of 10, 1 through 10. So it's centimeters, millimeters, meters, decimeters, whatever you want to call it. Okay, but we can establish the ruler any way we want. All right, does this make sense? How we can use that? Okay, so now where we tend to use this, why we'd ever have the ruler postulate. Sometimes when we're doing straight segments, they're asking for what would the number roughly be. So when you're actually measuring something, this object is 4 inches long using a ruler. That's using the ruler postulate. You're actually measuring something. That's why it's a postulate. There's no way to disprove that you measured it with a ruler. This is exactly 4 inches long, or that stick is exactly 3 inches. So that's why it's a postulate. We have to start somewhere, so they give us some form of measurement. So anytime you measure something on a picture with a ruler, you have to use this as your property. Why that works. Okay, we'll see this one later. Okay, now 2.9. Still a postulate, right? So we don't prove these because they're just something basic. Now this one gets a little more specific. This is something that's you should know how to do as of this moment. So here's the setup. If A, B, and C are collinear, now what does that mean? Collinear. They're on the same line. So they're on one straight line or segment, whatever you want to call it. Then point B is in between A and C. If and only if, so point B is in between A and C, if and only if this were to be true. That AB plus BC is equal to AC. What this is actually stating is that when you add segments together, it makes a bigger segment. Now why this is important, why this actually works, is because of that first line. They had to be in a straight line with each other. It can't be that little flex in the road. So the big idea here is segment addition. We're adding segments, right? So here's the picture. You have B is somewhere in between. It didn't say the middle, it's just in between A and C. When you add this little stick and this stick over here, BC, you make the entire stick AC. This is the first time you're actually seeing the postulate name for adding segments together. Now eventually we'll get to angles, where we can add angles together by the same thing. That'll be a different postulate. Now, the only reason why it works is because they make a straight line with each other. Now, I think what we talked about a long time ago, like chapter 1. Why do they have to be in a straight line? Why can't you do it for a picture like this? So here's M, here's O, and why isn't MN plus NO the same as MO? Yeah, it's a different line, right? MO, when you write this, where you use 2 letters and you don't put a bar above it, it means the shortest distance between M to O. That's this line. Okay, and this doesn't work. Like when you add this piece and this piece, it's not the same as this one. The reason being is that it's called a triangle congruence. That anytime you add two walls of a triangle, it should always be bigger than the third wall. Well, the common sense way for me to explain it is that imagine you're standing here and you want to walk home. The easiest way to do it is just walk straight home. Don't make any weird detours. Going around the block takes a lot longer distance. You're walking more steps than going straight home. That's why this doesn't work. Because you walking around the block should not be the same distance as you taking the shortcut. They should not be the same. That's the idea. So that's why the only way that math works is if it's like that straight line distance. You walk for a while, you take a break, you keep walking. And it's the same distance no matter what you do. Okay, questions with this concept. I think we've already discussed this. This is actually one of the parts in the first test, but we've never really seen the formal postulate for it. Now, what do you think the name of this segment or this postulate is called? Segment addition postulate. That's the name of it. So, we'll eventually get to angle addition. How you do that angle together, but that'll be later. We'll get to that. Actually, might be the next section. Actually. Okay, again, that only works because they're in a straight line. Okay, now the words if and only if, that's called the biconditional. I think what we talked about biconditionals long time ago is when we were doing conditional statements. We were talking about validity of a truth statement, right? Well, this idea of if and only if works. This thing works only if this first part was true, that they're in a straight line. It's a two-edged sword. So, all right, but that's the postulate. We'll see how to use that here in a second. But these are the two that I want to talk about today. Now, the theorem that we're going to talk about now, we do have to prove this. This theorem does have a name. There's actually three parts of it, so I'm just going to show you them, and we'll kind of discuss why this works. It's really straightforward. Okay, and you'll probably you won't realize like this is actually a theorem because you've already had it in your property sheet for a while. Okay, so this theorem relates to the reflexive property of congruence, which is this, where you set things equal to themselves. Right, that's reflexive. Now, instead of saying property of equality, this is now talking about congruence, where we can put geometry shapes congruent to each other. Because what we had earlier on your property sheet, we had properties of equality, right? Like x is equal to x. Well, what that is, that's an algebra problem. You know, setting algebra stuff. Well, this is talking about this idea of theorem 2.2 is applying this reflexive property to actual geometry parts here. So what are these objects? They're segments, right? They're sticks, they're lines. These objects are now congruent to each other. You can set actual physical objects equal to each other. That's going to be useful. I'm going to show you that here with another example. We have the symmetric property for congruence, so we can do that for geometry shapes. So if this segment is equal to another segment, then you can flip it around. It's still the same sentence. So again, we're learning that the properties of equality still apply to geometry shapes. That's what we're learning. And the last one is called the transcript problem of congruence, where this is the one where you have to look at daisy chain of events happening. If AB is equal to B or CD, CD is equal to EF, and AB is equal to EF, like the daisy chain of events occur. I do want to prove the last one, which is kind of weird. Like, how do you know that that's true? It's actually super simple. Just to prove like this idea of congruence, how that works. But again, the name of this thing is called the properties of segment congruence. So I'm using it for segments, but it's for any geometry congruence. But I want to prove this last one, this transcript property. How do you know that's true? So the first part with how you start a proof, this is going to seem silly, because we do have proof theorems. So I'm going to show you one of them. So I'll show you the last one, right? Line 1, we always start with what we're given. So AB, that segment, is congruent to CD, that segment, and CD is congruent to EF. And that's our given line. Notice I didn't write the last one. The last thing we're trying to prove is that AB is equal to EF. So we can't write that. That's my last line. Line number 2, what we always do for geometry. In fact, Trish, you even said it earlier. We always redefine what congruent means. So what does congruent mean? It means they're equal. So AB, that segment, whatever the length of it is equal to CD, that segment, and CD, that whatever that length is equal to EF. That's just congruent. Right? That's the definition of congruency. Definition of congruence. Or, I always put a little symbol down. That's what congruent means. These are equal. Well, now what this is actually is, these are just numbers now. Like AB, that's a number, CD is a number, those two numbers are equal. Right? Flush. CD is a number, EF's a number, they're equal. Well, since we have these back to numbers, so not actually geometry shapes anymore, this is actual digit on the picture, we can go to your property sheet, and since we know that these are equal, we can jump to the chase, and we can say that AB here is equal to EF, like the actual numbers themselves, the digits. So if 4 is equal to 4, 4 is equal to 4, so these two are equal, because they're the same digit. And why I can write that is called the transitive property of equality. So it's applied to normal like algebra problems, since those are just digits. And now I can jump to the chase where, since the digits are exactly the same, in line number 4, that means they're congruent to each other, because the distances are equal. So the actual segments are congruent, because that is the definition of congruence. That the measurements are the same, they're the same type of picture, so I can write that they're actually congruent to each other. Now, this seems really goofy, because you have to establish what congruence means, define it in line number 2, then you have to use those properties of equality that we learned on that property sheet that apply to just basic algebra problems, which these are algebra problems. And now that I have them, that they're equal to each other, now I can go back to congruent. And that's what I was trying to prove, that AB is congruent to EF in the very end. It seems goofy, but you have to show it for the first time that it actually works. To me, I always find this funny that books do this, because it's in every textbook. You can look at any geometry book that I have. To me, transitive is transitive. It doesn't matter if it's a geometry shape or it's an algebra shape. That's why I never stressed that you had to put transitive property of equality or symmetric property of equality. I just said you can write the word symmetric, transitive. It's the same thing. I don't know why they have to state this, that you have to define the difference between algebra and geometry, because these properties work the exact same. It doesn't matter how that works. Okay, I'm going to stop there today. What we're going to do tomorrow, we'll continue on right away tomorrow. We're actually going to do it like a geometry proof, like I was talking about earlier. We're going to try to show you how these apply, because we haven't really talked about these yet, especially reflexive or transitive. That's where I want to pick up tomorrow. Okay? Make sense? Okay. You have the rest of the time today where you can move around. You can work. I want you to work on that worksheet 2.6, 1 through 5 only. Do not work on the back. Only do the 1 through 5. Hey, just a reminder to all the girls in here, we have first day of basketball practice tonight. So if you're interested in going up for basketball, and maybe you forgot all about it, that's fine. Try to show up tomorrow. But I know some of you are like gone for builders and stuff, so that's fine. I know like Rachel, you're gone today. That's fine. So just let me know at some point if you're interested in going up for basketball. Show up this week, see if you like it or not. Oh yeah. So I'm just gonna try to remind the kids, especially if you like see girls in the hall, remind them they want to go out. Yeah, I think the first one is 3. Yeah, I think that's it. Because I don't think there's anything you can add to it, like terms. So.
Yeah, they're all different.
I got X minus 71.
No worries. Yeah, the first couple are you feel for.
They're like super easy, then the next one's gonna be like 20 million lines, and it's like.
I know how to do it. I just don't know any of the.
And I know how to do it, I just don't know like it's
Yeah,
or you do it.
study words.
No, I should like look at this.
Probably what you should be doing. Yeah.
Oh, my turn. I just like
Yeah, I got a bit of ours. Jack, you sit right here. It's all my shoes. What? What? No, I have honor code today. I don't put it on the line. That's pretty good. Hello. That's with my father. He needs to get paid. You're just so bad. Yeah, but I actually think you see them. You know what BBC stands for? It's not British broadcasting. She kept saying it too. You know, that's yeah, well, I did all of ours and I didn't know. What? Kind of going to I'm just also, I'm talking about paintball at one point.